So I was originally going to talk a little bit about, so like I'm a design engineer at Tailwind, whatever, but I was originally going to talk about why AI likes to write Tailwind so much. And that was kind of an excuse to talk about how AI works and shoehorn a little bit of compression, because Tailwind is actually just kind of compression when you think about it. But I didn't have time to write that talk. So instead, I'm going to talk about something that I've been writing about a lot lately, and that's how a screen works. And I know you're probably thinking like, okay, cool, why is this dude talking about hardware at what is essentially like a software-based meetup? But there's a bunch of like really interesting downstream software effects that are caused by the way screen hardware works. Things like color spaces, rasterization, anti-aliasing, these are all like byproducts of the hardware decisions we've made over the decades. But aside from that, I just think like it's fucking interesting. And and I think like the fact that we have digital displays is kind of like incredible at all. There's so many like just incredible innovations that had to happen that it's a miracle they made it out of the lab. So that's what we're going to talk about. I kind of think that like if we invented the transistor before the CRT, I don't think anyone is in this room right now. I think modern software just doesn't happen. But speaking about the CRT, let's go back to the beginning. Right, so the first like practical electronic display is the CRT, or cathode ray tube. And it was invented in 1897. Queen Victoria was on the throne when they invented this, which is just crazy. But by the 1950s, this is like a common household appliance. Besides like radios, this is like the first consumer electronic device that people had in their houses. I spoke a little bit about how this thing works at config, so if you've heard that, sorry. But the way they work is like bonkers to me. Essentially, it's a big glass vacuum tube that has an electron gun inside of it, and it fires a beam of electrons at the screen. And the screen is sort of coated in these tiny phosphorescent dots. And when the electron beam hits them, they like emit photons. The front glass is coated in lead because actually this thing's kind of like a mini X-ray gun. So the lead is there to stop you from like frying your brain. And so literally like for 50 years, like half a century, we all stared down the barrel of like a tiny X-ray machine for like hours at a time. Around the tube, like the neck of the tube, is a set of magnets that deflect the beam to different parts of the screen. So we can change the like voltage and manipulate the magnetic fields, and that like gives us precise control over where the electron beam goes. The whole thing happens in a vacuum tube so that the electrons aren't like deflected by the air, which is pretty crazy. But this is kind of where it gets a bit software related. I don't know why. There's some stuff that you can't see for some reason. But because you can only light up like one phosphor dot at a time, you have to render the image in sequence, like one pixel at a time. And so they came up with the idea of like just scanning left to right, like 50 times, between 50 and 60 times a second. And that has like a bunch of interesting consequences. So it means that you send the image signal, like this is an old school like television signal, imagine, being sent in sequence. But early computers like adopted this approach because it already existed. So in the very early days of computers, we would send the pixel value for each pixel in sequence, like one at a time from the CPU, which is like an insane thing to be doing. Because it takes like just a shitload of CPU capacity to be monitoring that like 50 times a second, right? So eventually what happens is we developed like dedicated video hardware just to manage that problem. And one of the things we developed is something called a frame buffer. Again, there's supposed to be stuff here, but imagine there's like ones and zeros over here. A frame buffer is essentially just a piece of RAM that stores all the red, green, and blue values for the entire display. Like every pixel just stored in RAM. And so the GPU can write to the frame buffer, and it only has to update the bits that have changed. So it doesn't have to like monitor the whole image the whole time. It just like writes to the parts that are different. And then the display controller reads from the frame buffer at the refresh rate of the display. The rate at which the GPU updates the frame is the frame rate, the difference between refresh rate and frame rate. Anyway, that's kind of wild to me that they figured that shit out. It's still pretty much how it works today, but for a while there was an alternate approach. Because memory was super expensive, so like storing the pixel values of everything back then was like crazy, and CPUs were still constrained, they had a completely different approach called a vector display, which is still a CRT, but instead of scanning like line by line, it would draw images like an SVG, basically. Like it would store the vector points and just arbitrarily move the electron beam around the screen. So it would draw like a font, kind of like this. And that used a lot less memory. You only need to store what's being displayed. You don't need to care about like this top left pixel that's just white. And they can skip like rasterization step and don't really need to worry about anti-aliasing because they were like monochrome and very tightly packed. But they're like more or less sucked in every other way. You couldn't draw like filled shapes. You can only draw lines. They have like very arbitrary refresh rates because you're moving the beam around very randomly. And so when memory became cheaper, the frame buffer approach sort of won out. But it's just kind of interesting to me that for a while, like pixels weren't the obvious solution. Like we just take them for granted now, but there was another way. Now, modern displays have like a fundamental difference compared to CRTs. And that's that they light up every pixel simultaneously instead of in sequence, right? Which is why that frame buffer approach has persisted so long, because you need all the pixel information for the next frame at once. Now, I'd say that the modern display war is sort of being fought between two main categories, right? Like OLEDs and LCDs are the two dominant technologies, but they really represent two fundamentally different ways of rendering an image. So an LCD, well, an OLED actually is self-emissive, kind of like a CRT, where the pixels produce their own light. But an LCD is transmissive, and that just means that it has a backlight, and it sort of filters the backlight to present the image. So basically an LCD pixel looks sort of like this. It's just a stack of layers, and each layer is about conditioning the light before it gets to the user. And they sort of start with a backlight. Again, can't see that. This is supposed to be yellow, but whatever. Start with a backlight, and then the next step is a polarizer. So a polarizer is sort of crucial because light is really weird. It's a wave and a particle at the same time, and the waves sort of come out like perpendicular to the direction of travel. And so a polarizer is just sort of like a big grate that filters out all the waves that aren't perfectly in line with the grate. And we need this because at this stage in the LCD, because we want the next stage to receive perfectly polarized light. The next stage is the liquid crystal stage, and this is one of those things where I just don't actually believe that we figured out how to do this. It doesn't make any sense. But essentially, like a liquid crystal is a crystal that can change, it's transparent crystal that can change its structure when exposed to electricity. Like, just think about it, like, what? In their default state, they're sort of arranged in a way that allows the light to be passed through. In fact, they like polarize the light in their own way. And when we apply voltage to them, we can shut off the light that goes through them. It's just like bonkers that's even a thing. This helix allows light through while changing the polarization. So you can see, like on the left here, light enters in one polarization and it twists through the helix structure and is polarized like 90 degrees. Just think about how random it is that we just found something that does this perfectly. Each subpixel has its own set of liquid crystals so that we can control like red, green, and blue individually. And there are a bunch of different types of liquid crystals that each have their own trade-offs. They're mainly like trading off refresh rate and viewing angles and stuff, but they more or less all work in the same way. So above the liquid crystal bank is a color filter. Filters out all the light that you don't want, so filters out the other spectrums, not red, green, and blue. And then the last step is a second polarizer, just to make sure that nothing gets through that made it through the stack. It shouldn't have. But even with advancements in LCDs, they sort of suck in a bunch of ways. Because they have this like Rube Goldberg machine sort of way of filtering light, they aren't perfectly light blocking. And so those like polarizers and the liquid crystals let a lot of light from the backlight bleed through the image. And so they can never get like really black. Manufacturers try to get around this by making like the backlight like thousands of tiny mini LED dimming zones and stuff, but you can still tell if you still see like fringing around the edge of like white things like that. And they also have really slow response times compared to OLEDs. That's because the crystals actually need time to like twist and untwist. And because of all the polarizers and stuff, they're only designed to be like looked at head on. If you move to the side, the brightness sort of fades and stuff. And so OLEDs are designed sort of like with the opposite set of constraints. In its simplest form, it's sort of like an organic sandwich. So you have these like organic emitter layers, and they are sandwiched between an anode and a cathode, and we pump electricity through it, and it makes light. But to be more accurate, it's actually a result of something called like electron-hole recombination. And that basically means like when an electron leaves its spot in the lattice, it creates a hole. And we put it back in the lattice, and it emits light. And the sort of like organic material you let it do that in determines the color of the light. Which again, like in the beginning I said how unlikely all of these discoveries are. This is like crazy that we have this in our pockets. It's bonkers. But so because each pixel emits its own light, they can be perfectly black because you just like turn them off. Super fast response times because there's no crystals to twist. Great viewing angles, all that sort of stuff. The big bummer with OLEDs is actually caused by the compounds themselves because they're organic, so they're like carbon-based. They just sort of stop working over time. And so that's why you get like burn-in on OLEDs after a while, especially if you've been running them at high brightness, because they can't get very bright compared to LCDs. And of course, like manufacturers have tried to like figure out ways to make this better. So like tiny little lenses to focus more light out of it, or like the more insane tandem OLED display, which is like literally just two OLEDs stacked on top of each other. But yeah, so that's sort of how screens work. That brings us sort of up to date. But you're probably like wondering, what all of this even means to any of you. But like I said at the beginning, there's a bunch of interesting downstream consequences that come from like understanding this technology. First of which is rasterization. This was like a big problem in the early days of computing because we didn't have high resolution displays. So you have to figure out like, okay, if the A sort of looks like that, like how do we fit it so that it doesn't look like completely different? And so fonts had font hinting in them, which like guided the rasterization steps so that like that lowercase a didn't look completely ridiculous, you know. There's other stuff like anti-aliasing, which is a consequence of like having pixels at all. There's a couple of approaches, like you can do grayscale anti-aliasing where you just turn off, or you just sort of like turn down some edge pixels so you have this gray line. Or you have subpixel anti-aliasing where you turn off subpixels so you get this like color fringing effect. But because usually it's quite small, human eyes don't really notice it and it's super effective. But also like color spaces in general are a consequence of having all these like diverging display technologies and the need for some sort of like standardized device independent way to do color. Not to mention like the way GPUs work is completely architected around the fact that we ended up in this like frame buffer pixel situation where we split the whole image up into fragments and process it simultaneously. But yeah, those are just some downstream consequences. Mainly, I just think it's kind of interesting how screens work, and I think we all just take them for granted. If you want, this was a condensed version of an article I wrote about screens. So if you found this too light on the detail, you can go read the full version at like makingsoftware.com.
You mentioned at the end that we kind of ended up in a place that maybe, I don't know, I'm assuming maybe it isn't entirely optimal. Is there something that you've seen that actually would fit way better with where technology has landed, or if we just framed it a slightly different way, that should be way better?
I think the main like drawback for where screens have gone is just like the resolution of curves and vectors and stuff. It always involves a compromise. As screens have gotten like higher and higher resolution, it's become less of an issue. And like the next generation of screens, they call them like micro LEDs, and they're like micrometer-sized LEDs. They're super tiny. So we are going towards a version where there's like pixels that are indistinguishable to humans, and then all of those sorts of problems like fitting stuff to grids sort of don't matter anymore. So I think we'll get there eventually, but I would have liked to see a world where we all had vector displays and it looked like asteroids all the time or whatever.
I'm just curious how you got onto this topic, if there was like a particular design. I mean, there's probably not something where you had a problem. I need to check the hardware here, but like, how did you get onto the topic?
I don't remember.
Sorry.
No, it's a great question. Mainly because I can't remember, but I remember maybe the thing that sparked it was I was looking into JPEG compression for some reason. I don't ask, but and I started to like really think about like, oh, I don't really understand. So for JPEG compression, they do this thing where they remove a bunch of color information because our eyes aren't really good at seeing differences between hues, but very good at seeing differences between like brightness, right? So they keep the brightness value the same, just remove some like color information. And I remember thinking like, I don't actually have a good grasp on like how screens work and like how any of this happened, like what am I seeing to begin with? And I think that's probably how I got into it. But I've always been sort of interested in screens. I studied photography, so maybe that's a shorter answer.
I just really love the illustration style that you have.
Thanks,
I'm wondering like how you make them and what it looks like behind the scenes, if you have any special like techniques.
There's no special technique. Do we have a minute and I can just like pull up a file?
Yeah, go for it.
It's surprisingly manual. I think that's the boring part, but It's all made in Figma.
Any plugins for like the patterns or anything like that?
Like it used to be plugins for patterns, but now patterns are part of like Figma Draw or whatever. I usually like Google some scientific papers on the topic and figure out like how they illustrate stuff, and then try break down what I think is going to be a good image. But I use primarily this plugin called Skew, which is pretty awesome. And it allows you to like rotate stuff at like a bunch of different angles. And it stores that information on the node, so you can come back to it and like alter it later, which is really helpful. And then I'll keep doing that until I have the rough shape right, and then at the end I usually have to like break it down into outlines and vectors and stuff and trim it all off, and then the skew just quits. So you like I'll do a couple versions, make sure it's right, and then sort of do something like this where I convert it into strokes and cut shapes out of it and do all that sort of stuff. But it's surprisingly manual. Like there's a fingerprint that I literally like traced. So I mean, that's it. It's harder than it looks, but it's simple.
So you don't actually draw like at the perspective isometric. You just draw like flat layers, and then you use this plugin to.
Sort of, yeah. I'll like figure out the architecture first, and then put it into that space, and you can carry on drawing in that space once you've figured out the angle or whatever. Yeah, that's about it.
What are the things that have thickness?
Yeah, what about them?
Like the skew is only like one plane, right?
Yeah. Oh, you mean like this? Yeah. So
it has, like, thickness.
That's what I mean when I say like I lay them out sort of flat, and then I have to change the actual like vector structure underneath by.
Oh yeah, so you draw the thickness yourself.
So in this case, if you want to add thickness, you take two rectangles, you sort of distance them apart, copy the vector structure from one into the other, draw the lines between them.